Yep, I'll just get started and see if I can actually control it from this other window. Aha! Okay, so the American fuzzy lot, AFL, is a breed of rabbit native to North America, descended from the Holland lot sometime in the last 100 years. So I think it may have been crossed with the English spot. They're very famous for the high fuzz content of their wool and the very high wool output, so they're bred for that. So in this talk, we'll learn about the various methods used to test and assess the quality of said fuzz.
Is it the model for your beard?
Or maybe not. Much more appropriate for the topic of the talk, here we have the killer rabbit of Kerbanog from Monty Python and the Holy Grail. AFL is a tool that allows you to perform fuzz testing against your whatever program. Oh, yep. AFL is a tool that allows you to generates input for fuzz testing your applications and captures it for you. This talk's an intro to fuzzing in general, as well as a specific demo of the particular tool, AFL. I seem to have forgotten the mic. All right, so nobody got my funny intro. Oh well. There we go. Okay, so why am I interested in this thing? I'm a massive programming language theory, and like correctness nut really bothers me if I'm not sure that my program is doing the right thing. So testing can only prove the presence of bugs rather than their absence. That leaves me somewhat annoyed. I spent most of my career writing C++, Python or Go. C++ specifically, not known for being the most correct of programming languages. It's very easy to shoot yourself in the foot, get memory unsafety errors, stuff that should run perfect, or stuff that you think runs, does run and runs for months at a time and then randomly blows up somewhere in a customer's network, or in my case, on a camera deployed in some remote observatory somewhere. So I really would prefer if the stuff was battle hardened before it went out into production, but that's kind of a contradiction in terms. You can't really have something that's battle hardened until it's gone into battle. Well, fuzz testing gives us a way of simulating the real world. In fact, possibly something more hostile than the real world. Also, I'm terrible at thinking up edge cases. If I'm reading my code, I'm looking at it going like, yeah, I wrote that. That does exactly what I expected to do. There's no way that there's any, I've missed anything there. Why might you be interested? Either for similar reasons to the above, or just for the fact that fuzz testing allows you, because it is you're fuzzing the program, you're throwing random input at it, it actually allows you to, it'll find a bunch of bugs, hopefully, or actually hopefully not, but generally it does. It catches difficult, hard to find bugs, or bugs that are related to things you'd never think to test, because the machine thinks very differently from you as the programmer, or even you as the test engineer or QA person or whatever. And also it can generate test cases for you. If you start off with a program and you want to see how it works, or if you want to generate a bunch of like external black box tests for it, there's worse things you can do than just run a fuzzer against it and get a huge big corpus of things you know work now, like hey presto regression test set. So yeah, so what is fuzz testing in more detail? And how is it different from your sort of normal run-of-the-mill testing that everybody's familiar with? At least I hope everybody's familiar with. If anybody in the room hasn't drank the Kool-Aid and is looking to be like convinced to write tests, then sorry, not the talk for you. Yeah, so normal testing, manual testing, how is it different from those? In your general approach to testing, you tend to look at your program, either read what it does or read the documentation for it, and then start thinking up example cases that should do what it says, essentially. So you'll come up with you have an HTTP API, you'll look at the docs, you see what a valid input to this looks like. You may then start tweaking it or leaving bits out, or even just writing valid ones to make sure that it does in fact do what it says it'll do. That's how most people approach testing. You generally work from the happy path backwards. usually, unless you're a specialist doing exploratory testing. Fuzz testing does the complete opposite. It works from completely random input. You can, and you should, generally give the fuzz testing tool some sort of hint as to what valid input looks like, so that it doesn't spend a whole lot of time generating completely useless input. But generally it comes at it from, here is completely random fluff, let's see what happens. That might be a wee bit familiar to you, especially if you've come to some of my talks before about property testing, hypothesis, or quick check or anything like that. It's not totally dissimilar to property testing. In property testing, you're not giving example cases, you're giving general properties that your program should abide by. So if you were testing like a list reversal function, you'd test that the output list was the same length as the input, that kind of thing. And then you do you allow the machine to throw random examples at it and test if those properties still hold. But that still requires quite a lot of human creativity to actually come up with the properties and to work out, in an abstract way, what should this be doing? That's a really sort of high-level abstract bit of thought that a machine is not great at. I do not know what just happened to that.
Did that switch off? Did it overheat or something?
Possibly. I don't think I stepped on anything.
Well, it looks like it switched off because it's yellow.
Yeah.
Usually green is good.
Yeah, it's flashing off up here, so the projector may just have decided that it wants to have a nap. Oh well. Maybe not. I could try.
It's still running, it's not too hot. I will do it. Keep the lamp cool.
Yeah. Interesting. Okay. Well.
Too hot for the projector, eh?
Oh well, you won't have the advantage of my nice funny pictures, but yeah.
We can always gather around.
Yeah. We'll keep poking at this until it turns back on, but in the meantime, I'll keep talking. So a little bit it's very different from property testing because you don't have to think quite so, in fact, you don't have to think at all for fuzz testing. Property testing requires quite a bit of abstract thought. And also property testing tends to be used on very small sort of isolated components where you want to test a function behaves this way because testing properties of your entire system tends to reduce, oh, it just went green, tends to reduce down to does it crash or does it not crash, which fuzz testing is actually perfect for. So I don't know why I'm advancing my slides, but whatever. Yeah, the little bit of the history of fuzz testing, it doesn't come up a lot in a lot of the current practices and literature, or else it's always sort of relegated to a sideshow, but it's actually been around for a very long time. There's easily back beyond the dawn of computing proper, we've had fuzz testing. It was probably called random testing or something else at the time, but even right back into the era of punch cards, there's documented examples of programmers or whatever operators who configured large punch card engines going off and grabbing ones out of the trash and putting it into the machine to see if the machine continued functioning properly. If it didn't, then there's a bug in their configuration. So it goes back ages and ages. One of the earliest examples of a actual fuzz tester was, I think it was written for Mac OS in about the 1984, 1985, something like that, to test Mac Paint, and it just generated random image formats and saw if it would load them, watched whenever it crashed horribly because it was written in C and was dealing with file formats. So yeah, why isn't it really common practice now? Traditionally, fuzz testing has been really slow. You would have an entire big cluster of computers dedicated to fuzzing some library, and it would take absolutely ages to produce not very many results. You either need to give it really good examples, in which case you might as well just be doing example-based testing and having a person sit there and stare at it anyway, or else you had to have actual clusters, and there's generally something more useful you can do with a cluster of machines than throw random inputs at a program for a very, very low like exchange rate for actually finding things. So, and even then, if you did provide good examples, it was still very, very slow. So, enter AFL. Technically, this is not an American fuzzy lop, this is a Holland lop, but it was far, far too cute for me to not put that picture up. So, enter AFL. AFL is a modern, as in, I think it's first released publicly in about 2008 or so, open source fuzz testing tool. It's very different from the traditional ones. Not just in that it has a awesome retro UI, but also that it is intelligent compared to the ones historically. So by intelligent, I mean that it doesn't just throw completely random input at the program. It's sure you can give it some seed input to give it an idea, but then it will watch the program executing. Traditionally, fuzz testing was just a black box where you had a program, stuff throwing at it. Did it crash? Did it not? Yeah. AFL takes advantage of a lot of the advances in compiler tech and interpreter metrics gathering that developed through the sort of 2000s, mid-2000s. So, like for example, if you've ever done C or C++ programming and you've wanted coverage coverage information out of your test suite, you actually have to compile it a slightly different way, and that inserts some instrumentation in around branch points. So for everywhere there's an if statement, the compiler will actually sneakily insert a little counter where it increments it, decrements it, whatever, to show that you've actually gone past this, you've gone down into this branch of the if statement, etc. AFL leverages that to be able to actually follow or to see how much of the program it has explored. So it will still be throwing random inputs at the entry point, but it will then be watching to see what bits of the code are being executed, and if it finds a way down a new path, it'll remember that for next time and use that as its seed to then progress out and search the rest of the program from there. So rather than just hammering a black wall or hammering the wall, it actually, or the black box of it can actually look in behind to see how far its inputs are getting. So it's a lot faster at finding examples, and it massively increases the functional coverage of your code compared to the traditional fuzz testers. It also has a bunch of fun stuff, like it uses genetic algorithms under the hood, and it's taken a bunch of the academic research into fuzz testing over the past 20, 30 years and applied it all in this nice little package, and it is extremely easy to use. It doesn't have the massive number of configuration options that other similar or older tools would have. It basically just does the right thing off the bat, which is excellent, especially whenever if you just want to throw this at your program. It's pretty much trivial. It's also really useful for, as I said earlier, generating input test cases or regression test cases or whatever you want, to then have a human sit down, look at and go, oh, okay, that's caused a problem or whatever, and be able to turn that into a better test suite with some human intervention, more resource intensive techniques, etc. It's also supported by a whole load of languages, so it's like Rust, Haskell, Go, some weird esoteric languages like C, C++, Python, JavaScript, Ruby, whatever. But importantly, like Rust, Haskell, Go, perfect support. And it has a really good track record. So can anyone tell me what that logo is? What? Yeah. So AFL actually found shell shock. There was somebody running it against the Unix core utils, and it wasn't just shell shock, found like 20 or 30 security vulnerabilities, but I'm pretty sure that shell shock was the only remote code execution vulnerability they found in that pass. But that was found by AFL just running against random things. There's a whole big trophy case of it that I might bring up, depending on. So it didn't initially find Heartbleed, but they reproduced the Heartbleed discovery in AFL within a couple of days, and then set about pointing it at pretty much any network system they could find. And they found a whole bunch of other remote code execution vulnerabilities, not remote code execution, data leak vulnerabilities from other systems based on the reproduction steps they took to train it to find Heartbleed. So that's kind of cool. Let's see if I can bring up the trophy case. I'll save it for later, but there's like hundreds and hundreds of bugs. If you go down the page, there's like 3 against libjpeg, 2 against Firefox, hundreds against ImageMagick, etc., etc. So it works. It's very good at what it does. So now for the really dangerous bit. I'm going to try and demo this. So I think that means that I'll need to put that on a different screen. And then, right, okay. Can everyone see that? Is that big enough? I may actually shrink it a wee bit because, yeah, okay. 4x3 does not work well whenever you have a long shell prompt. But okay, so I'm in a Git repo here for it's a library I've been writing recently that's a parser for the ledger file format. If anyone's ever come across it, it's a command line accounting tool. I've decided to write a parser for it in Rust because I want to learn how to use parser combinators in Rust. So I've been working on this for the past couple of months. It's, as with most things when I'm learning it, doesn't have brilliant test coverage. So let's see, here we have our standard Rust project layouts. So you have the cargo TLML, cargo lock, and then the source directory is what we actually care about here. So let's see what we've got in here. Oh good, I'm in the right one. This lib.rs has, yeah, hundreds of lines of stuff. Oh, that's not what I wanted. Oh, right, okay, it actually has a pager. Nice. Also, this is a tool called BAT, which is also written in Rust that does syntax highlighting for like printing out files. So yeah, there's quite a lot of code here, and not very much of it is tests. I think if I get right down to the bottom, yeah, I have like 2 pages of tests here compared to the hundreds and hundreds of lines above it. So I would quite like to know if I can run cargo test and see if that's working. So, oh, tests are all passing. Sure, that means there's no bugs, right? Let's see what happens whenever I go down in here. So here I have a little sub-project, which again has its own package manifest and basically build description metadata. Inside the source file here, I have a tiny, tiny little application that loads my big library there and does not a tremendous amount of stuff. I'm going to have to take the mic off to come and point at this, but yep. So this is all you need to get up and go with fuzz testing in Rust for Python, for C, etc. It's all very similar. So just your normal inputs at the top, or your imports at the top here to pull in the library I want to test, some setup stuff, and then the AFL fuzz macro. And then all I do is call that fuzz macro, give it an anonymous function that takes in some data, which the fuzz macro sets up to read in from standard in. So everything is done by just AFL just popping up a sub-process and writing random input across it. Tries to convert it into UTF-8 data because I'm not interested in parsing raw bytes because that's way lies madness. And then just calls the parse function on my using the unwrapped string. So that's all you need. That's all the code you need to write in order to get your system ready to get your library under a fuzz tester. Okay, I'm gonna run this command. So it's just two commands. First, there's a handy helper for Cargo, the Rust package manager, that will do it. Basically, just set some compiler flags to set the coverage instrumentation on for whatever you're building. So it just sits there in the middle and gives you a handy way to do that. You can do this raw if you want by setting a bunch of Rust C command flags or C, or I think the Python interpreter one, you have to import something at the start of the script, and that's how it gathers the coverage information. But yeah, here, it would help my mouse wasn't in the way. Yeah, so here I'm just going to build the projects with AFL, and then I'm going to call fuzz, and I'm going to give it some examples from an input directory, which I'll show you in a second, tell it where to write its output, and tell it what to actually call in order to, what binary to run, and that there target slash debug slash ledger parse fuzz target is the binary I'm going to run. So first thing, yep. Okay, so built that very, very quickly. Then that pops up, tells you some information about what the run's about to do. And, right, how smart's the, oh, very good. So, cool, fun retro UI. That number up there, the larger one that's incrementing slowly, is the total number of test cases being run, or total number of runs that went down an interesting path, as far as I can remember. The stage here is telling you what various different heuristics and what different deformations of the input it's using. So it's like how it's generating the next step. So like bit flip ones and arithmetic, and there's one called Havoc, which whenever you aren't finding errors, it tends to run Havoc a lot because it's just trying anything to see if it can get something strange. What we have here, these 17 unique, are actually, so it's found 971 inputs, or about whatever inputs that make my parser library crash. It's found 21 unique ways of doing that, so that's 21 different ways of getting down that path to make it crash, or down a path to make it crash. If you remember, my unit tests were all passing. And that's the, yeah, there's various other things there about the number of runs it's used, the like just interesting data about it. You can check out the documentation for exactly what those all mean. So I'm going to kill this now because it will just run forever. You can leave this running overnight. You can leave it running on a cluster somewhere. It'll just run and investigate as much of the program as it possibly can. It's going to be a really weird video. There's going to be audio for about a quarter of it. Okay, so if you remember right, I'll just clear that. If you remember, I told it to read examples from in. So if I do this, yep. So I have a bunch of example files there. So I am just going to, actually I wonder if BAT has ledger support. Nope, doesn't know how to read them. Anyway, so that's what a ledger file looks like. Though it's using all of those as its example input, and then just changing random bits off them in order to generate its random test cases. Now, if we look at the out directory, we can see that there's a couple of folders, a couple of files containing stats that I have never actually looked at because I've only ever been interested in the crashes. And that is all of the files in there that produce, these will contain some sort of input that caused it to crash. So we'll pick a random one. ID. Yep. There you go. So, wonder what this one did to make it crash. We'll have a look at it. I actually have no idea. This is completely random generated, so this is me trying to diagnose on the fly. I'm going to guess that there was previously minus 3.5, and it has just changed that to a quote, which has broke the parser, and somehow that has led it down a path. somehow that's went down a path where it's crashed. Okay, that's a bug. Right, I have an extra bug. So I deliberately hamstrung my program, but I'm going to have to keep that one around and look at it. But I deliberately hamstrung the program, and I can tell you exactly where it was failing because I stuck in an explosive panic somewhere. Yeah, so I have that panic sitting there, and if anything comes down and there is a signed amount coming through, it just panics by default rather than producing the correct thing. So I'm going to delete that line and and try and run it again, see what happens. Hopefully this time it shouldn't find anything, but it might because I'm not actually sure about that. So this is it, goes off, rebuilds the dependency because it's a local dependency, runs the same thing again, and hopefully this, oh, damn it. Yeah, hopefully this time nothing should turn up, but if it does, so that's, I'm just going to leave that running and see if it turns up that, because I'm quite curious. Yeah, that's what AFL looks like whenever it's running. I will pop this back over onto here. As you saw from that out folder, as you saw from that out folder, it dumps out the files containing the input, so you can then take those and do whatever you want with them. General conclusions that I draw from this is fuzzing's really, really good for catching subtle bugs. Really slightly annoying whenever you're not expecting them. It thinks, the machine can think in a way that a person just doesn't. That there one that you saw where it had just transposed a 3 with a quote mark, okay, a person may have thought to do that, but you'll get interesting ones where it'll generate inputs so long that it causes a buffer overflow somewhere, or it causes a wraparound on an index, which a person's never going to think of, or it'll just, by exhaustively searching, it will pick some length of input that happens to, if there's a modulus operator somewhere, it'll get it and cause a 0 to appear somewhere, and that will go on and trigger another thing, and eventually you get down to a point where it just crashes, or seg faults, or does something really strange in an underlying runtime library. If you want your code to be robust and you don't want to come out on call for a 3 a.m. random null pointer exception, this is a brilliant type of tool to have in your arsenal. And as you saw there, that took me 6-7 lines of code to build to get AFL running against my library. It's really, really easy to do. It's very quick. If there is a bug, it's very quick at finding it. And yeah, that's pretty much it.